for the exchange among the community. Be delighted to give my presentation today entitled Application of Remote Sensing and Air Quality Monitoring. May I just start by reminding everybody of the importance of air quality and talk a bit about the Air Quality Index and its components, air quality monitoring stations, then get into the remote sensing aspect of it and why do we need to use remote sensing at all? Why don't just rely on what we have so far? Talk about, just present a couple of common sensors and products that are valuable for such activity. Then talk a bit about the PM 2.5 and PM 10 estimation, and finish with a short case study where we use MODIS aerosol product to estimate PM 10 in the Lane region. And then finish with some conclusions as well. All right. So first, air pollution. And actually, rather than doing my own slide, I borrowed a slide from the University of Washington because I thought this slide, even though it's old, it presents a study that was published in the Lancet in 2013. It is still very valuable, very valid, and gets the point straight to the audience. What this graph or what this map shows actually is the rate of mortality mainly due to air pollution. And in 2013, actually, air pollution or the ambient air pollution was responsible for about 5.5 million deaths in the world. This is a huge number. That is worrisome. It presented actually the fourth factor or the fourth risk factor for death in that year. And if you look at the map, actually countries that are the most affected are China and India, and these are countries that have traditionally been under a lot of air pollution and bad air quality. So this by itself gives us the motivation mainly to ensure that for our sustainability, for the sustainability of our society, we need to be careful about air pollution and about maintaining a healthy environment for the inhabitants. This has been reiterated by the United Nations Sustainable Development Goals, SDGs, as they are referred to. So it's mainly a plan of action for everybody to sign up for, to act upon, to collaborate, to implement, and so that we can ensure that our good being and the continuation of our mainly quality of life in the future. So there are 17 SDGs in this plan with about 170 targets. What's relevant to air quality, actually, I circled two goals. Number 3, which is good health and well-being. And as a matter of fact, one of the indicators of this goal for accomplishing this goal is mainly the mortality rate due to pollution, both ambient and household pollution. Number 11 as well, sustainable cities and communities. And again, there's an indicator there that mainly looks at the annual levels of fine particulate matter, both PM 2.5 and PM 10. And these, as we'll see in a minute, these are major components in monitoring air quality, understanding air quality, and making sure that we continue to enjoy the quality of life that we have at this point. Right. An indicator of air quality or a measure of air quality actually is the air quality index. The UE has established its an air quality index mainly based on a couple of components that I'll talk about in a minute. If you look at this map, what you see is numbers in different colors. So we can guess that green is good, red is bad, and well, what's in between is between good and bad, maybe. And that's completely true. So this indicator is mainly done or has been established to ensure that we understand the quality of the air in the environment or in the community we live in. It was created in a matter that commoners can understand it, can realize what it means. And there are different categories. Mainly these categories are fairly standard internationally. These are mainly the EPA standards. So values that are in green, which is value between 0 and 50, mainly may mean that everything is okay. The air quality is good. It's at its best, I would say. In yellow, up to 100, this is still acceptable. As we move into the orange, through the maroon, that's where the air quality actually is of lower standard, or presents a risk. Start with for certain component of the community, for people with health problems, the elderly, and then as we move more towards the red or the purple and the maroon, that's where the air quality is considered as a health risk for everybody. So how is this index calculated? Well, it's calculated using 5 major air pollutants. The particulate matter itself, and I'll be talking about that a bit more later on. Nitrogen dioxide, carbon monoxide, sulfur dioxide, and ground level ozone. So mainly the UE mainly it strives to ensure that we continue to live in a safe environment, has developed national ambient air quality standards, and the limits or the thresholds for these 5 pollutants are listed in the table on the right, the upper table on the right. So as you can see, there are maximum values that were set as not to be exceeded, or where exceeding these values will make sure that the color of our indicator will change from yellow to a riskier color. So again, so to calculate the AQI, or the air quality index, we look at the component having the highest ratio of concentration to the limit concentration, and that's expressed usually in percentage. So we look at any point, we look at the concentration of these pollutants, we divide by the limit, multiply by 100, and that gives us a number. The highest of those numbers is what is represented by what is mainly displayed on the map as the air quality indicator, and alerts people that we are going into dangerous zones. Right. So since it's a percentage, all values below 100 are considered as satisfactory, as safe, because that's the threshold we set. Values above 100 become risky for certain people, and then for everybody ultimately. So if again, we look again at the air quality index, and actually this was for yesterday at 10 a.m. Don't have time to do it for today, so I did for yesterday. If you look at those index, the National Center of Meteorology actually gives you all 5 components that are included in the index or that are used to calculate the index in addition to the index. By the way, you notice that here we use the PM10. Well, it's because we are in an arid area where particulate matters come primarily from desert dust, which are large particles. And you'll see this is what goes under PM10. Just if you look at the Western region, there's a number. I'm not sure I have the pointer turned on. Let's see. Well, anyway, it's obvious. See, there's a number in red over here in the Western region showing an AQI of 159. So if you look around at the different component, you'll notice that this number comes mainly from the particulate matter from PM10, which has a value of 238. The limit for that daily PM10 was 150. So you do the math, you do the ratio, and that gives you a value of 159%, which is a high risk value. So we have these different components that we need to measure to determine the quality or to calculate the air quality index. And this is done traditionally. This is done by using mainly stations like the one shown on this map, and using sensors, a variety of sensors that calculate or that measure these different components. Well, those stations have to be ground-based. They measure the concentration at ground level, which is what we really need for this calculation. However, what this also means is that they are not infinite. They are not. We don't have those stations implemented everywhere, and that's where remote sensing actually comes in play. So if we look at the map that I borrowed from openairquality.org, showing the distribution of air monitoring stations worldwide. It's the map on the upper left. You notice that there are a lot of gaps in that map. A lot of areas are not covered by these stations or have low density of these stations. So you'd say, well, okay, if these areas are remote areas are not heavily populated or not populated at all, then that's not an issue. And that's why we compare that to the population density. And you notice that there are some highly populated areas that are actually not covered enough with these stations. You'd notice that developed countries usually have a high density of these stations, especially in urban centers, in areas where we have people, where there are high population densities, whereas many other countries do not have that luxury. And so we have a gap in that measurement worldwide. If we need to monitor the air quality globally, then we need to either increase the density of these stations or rely on another source. And that other source can be remote sensing. So mainly our starting points and our accurate measurements are the ground measurements themselves. We have indicators, we have parameters that are measured by remote sensing. And then can we somehow tie these together through the use of models? Can we have our remote sensing observation mainly replicate or estimate the ground measurements that are mainly that we get through these sensors? And this is how air pollution monitoring actually is heading, or has headed in that direction, using supplementing limited number of stations, mainly to fill the gaps by the use of remote sensing indicators. So a couple of studies are out there. Look at mainly filling these gaps. Selected a study by Van Donkelaar in 2010, where he estimated the PM 2.5, it's fine, just the fine particle concentrations using remote sensing, just relying on aerosol products from remote sensing that I'm going to present later. And as you noticed now, our map that had a lot of gaps, when we supplement that with remote sensing, mainly becomes almost full. We can get observation, or we can get measurement or estimates of this particular component, the PM 2.5 here, everywhere. So the question is, are there enough measurements from remote sensing to fulfill the other components, or probably more urgently is how accurate and how can we get these estimates even for particulate matter? So what we know is for sure is that remote sensing does not measure these components directly. What I always tell my students is remote sensing, we have sensors that's recording, that's measuring radiation. It's just looking at, it's detecting the spectral radiance or the radiance that it hits its detectors and converting that into a number that we can use to infer other information or to derive other parameters, other biophysical parameters that can be used in our applications. So to do that, we need to understand what are what's the effect of that radiation as interacts with the atmosphere, as interacts with the different components, and understand the effect of the different factors that lead to the radiance that we measure at the sensor level. And that's the process we use mainly to derive our products. So we start with the parameters, with the spectral radiances that are measured at the sensor level. Then we use our information from ground measurement, from the radiative transfer theory on how that, what is affecting these measurements and how do they relate to the parameters that we are interested in. And that enables us to develop algorithms that produce the parameters or the indicators that we can use in our application. Particulate matter is an example of those. The concentration of particulate matter is an example of indicators that can be derived from remote sensing data using this intermediate knowledge. Now, do we have enough? Question is, does remote sensing cover enough ground and enough frequency to enable us to do this or to include this in our studies or in our air quality monitoring? And here we just summarized. It's not an exhaustive list, it's just a summary of commonly used sensors for air quality. So MODIS, the modern resolution imaging spectrophotometer, is a sensor that has 36 bands that enable the retrieval of total aerosol optical depth. And I'll explain what this is later on, because this is the one I want to work with for my case study. So this sensor is present on two platforms, Terra and Aqua, that were launched respectively in 1999 and 2002. Spatial resolution for the aerosol product varies from 1 kilometer to 10 kilometer. So you'd say this sounds like a coarse spatial resolution. However, for atmospheric events, for the atmosphere, these resolution are more than enough. Actually, are considered as in many models are considered as high spatial resolution. The temporal resolution or frequency of these measurements is daily. So we have actually with both platforms, we have a measurement twice a day, morning and afternoon. Aura, which has the ozone monitoring instrument, OMI, provides products like total and tropospheric ozone, sulfur dioxide, total sulfur dioxide, and total column of nitrogen dioxide. So the resolution here is a bit coarser as well. It's 13 to 20 by 25 kilometers, but it has a high temporal resolution daily acquisition. Now notice that these three instruments, Terra, Aquan, and Aura, are part of NASA's Earth Observing System. So these are the three platforms that were monitored or were developed to monitor the health of the planet for applications in the just the fourth spheres of the Earth: atmosphere, lithosphere, the biosphere, and the oceans. So these data are available, have been available since the launch and the start of production of for these three instruments, and are publicly available. So no need to worry about purchasing the data. It's already there. The continuation mission for MODIS mainly came in the form of the Visible Infrared Imaging Radiometer Suite, or VIRS, which currently is on board of two platforms, the NPP and JPSS, or NOAA 20, as people still prefer to refer to it, which were launched in 2011 and 2017, and again provides total column aerosol optical thickness or depth and aerosol type at the resolution of 6 kilometers. More recent instruments, Sentinel 5P tropospheric monitoring instrument, or TROPOMI, provides again gases in concentration, just total and tropospheric columns of ozone, sulfur dioxide, nitrogen dioxide, and carbon monoxide at a finer spatial resolution, and still at the daily level. So we have daily coverage, maybe covering all the parameters, all 5 parameters that we need to calculate our air quality index. And so there, that's appealing. That's what attracted scientists try to look at these types of measurements. So that's some examples of these measurements, just to show how they reflect what the changes that are happening on the ground. So first example is the sulfur dioxide concentrations derived from OMI on 24th of October 2016. And I have a feeling that I got the date wrong. It should be 2018, I think. So this is when we have the fire in Mishrak sulfur plant in Iraq. So MODIS true color composite actually shows the white plume of sulfur just leaving that plant 2 days after the fire started. But if you look at the concentration, the sulfur dioxide concentration derived by OMI 2 days later, see how that poisonous plume is spreading over the country and moving to adjacent countries. So this is something that that will affect definitely the air quality index. Sulfur dioxide comes from volcanic eruptions as well. So it's an example of a sulfur dioxide product derived from TROPOMI. for showing the plume of sulfur dioxide, mainly that was injected in the atmosphere from the eruption of La Sofia volcano in St. Vincent, which is mainly of almost an island, say, off the coast of Venezuela. And you see that plume has been moving eastward just to go over Africa and reach Asia as well. So this image was acquired on 15th of April, 2021. The eruption itself occurred end of December 2022. It's not 4 months later, or a bit less than 4 months later. In addition to that volcanic eruption, you've noticed in some concentration over South Africa, and these are mainly from chemical plants in there. Carbon monoxide can also be derived from tropomi, this example showing the average carbon monoxide mixing ratio derived in November 2017, so it's taking just period 13, almost a week in November, and it mainly shows the effect of wildfires in Brazil that raises the concentration of CO, and in Africa, but also the anthropogenic pollution in India and China as well. So again, these can be parameters that can feed our index and be used in the calculations of air quality, of the AQI. Last component, or the last case component, is nitrogen dioxide. And an example of that is presented from OMI for a daily image. Well, you know here that the image is not complete, and this is due to the fact how OMI works. We have gaps between orbits. So this can easily be rectified by mainly compositing multiple days, or 2 days will enable us to have a global image of this component. So then the component that remains is the particulate matters, which is mainly tiny solid and liquid particles that are suspended in the atmosphere. We call them aerosols or particulate matter. It's referring to them is the same thing. So these are very small particles with diameters, with the diameter less than 2.5 micrometer are considered as fine particles, and we denote them PM 2.5, whereas particles with diameters between 2.5 and 10 micrometers are considered coarse particles, and these are PM 10. So dust from the desert typically produces coarse particles in that category. So while the particles are too small to be seen by eye, their effects is visible, and actually we are all aware probably of the effects. Just if you look around on a dusty day, you notice that everything looks different. Just the sky looks grayish. You don't see clearly around. And so this example here is an example extracted actually from a site that has a nice tutorial on aerosols, showing pictures taken in Pittsburgh in the US, and Pennsylvania in the US, from the same location on 2 different days, a clear day and a hazy day. Sorry, and a hazy day, and you see that how just visually we can detect the presence of these particulates in the atmosphere. So if our eyes, which are limited mainly to seeing the visible light, can detect these changes, remote sensing instruments can definitely do it. And the way remote sensing instruments usually look at aerosols and assess aerosols is by looking at their effect as they travel through the atmosphere. One measure that gives you that is the aerosol optical depth, which mainly gives you the amount of light that is removed from a beam of light as it travels through a medium, in our case, the atmosphere. So if you look at the light coming from the sun through the atmosphere, hitting a sensor at the ground level, how much of that light was lost in its travel through the atmosphere, how much it got attenuated, is mainly what corresponds to, or what can be measured by the optical thickness, which we denote tau. There's a model that mainly looks at how much of the light is changed or is reduced following an exponential equation. The thing is that extinction in the radiation is not only due to the atmosphere. It's due to other factors, to the molecular scattering, to the absorption by other gases in the atmosphere. Aerosol is just one part. So the total optical depth that we measure by using this model is include these other two, or these probably there's other factors that represent an uncertainty in the model. So what's called aerosol optical depth is the tau due to aerosols, which I denoted here, tau sub AER. This is also called aerosol optical thickness. Now, radiative transfer theory can help us actually calculate the contribution of Rayleigh and other gases in the atmosphere. As we know, more concentrations which are less variable than aerosols. So we end up with mainly one big unknown, which is the aerosol concentration. And so that enables us to isolate through certain algorithm, the aerosol component and determine its aerosol optical depth. So the values that we see for aerosol optical depth are mainly correspond to the amount of pollution that we have. So the amount of the concentration of particular particulate matter that is suspended in the atmosphere, having values of 0.02, for example, means you're looking at the very clean, isolated areas. Having a values of 0.2 is fairly clean. 0.6, we start having pollution in the atmosphere, having concentrations. Heavy smoke or dust events will lead to AODs above 1.5, and if you have an AOD above 3, that means we cannot see the sun. Another thing to know about AOD is that other than the fact that we call it AOT sometimes, which is aerosol optical thickness, is that it's spectral. That means it varies with wavelength, different for different wavelengths. And this variation depends on mainly the nature of the particulates that we have. So it changes whether they are smaller in size or larger in size. So this is used to try to estimate the type of aerosols or the type of particulate matter that we are looking at. And this is done through the use of we call the angstrom exponent, which describes, supposed to be alpha instead of A, which describe this dependency of wavelength. So the easiest way to express it is we say the ratio of the optical thickness at two different wavelengths is equal to the ratio of the wavelengths to the power alpha, which is the angstrom exponent. If you determine an angstrom exponent less than 1, that means you're dealing with with a mixture with predominance of coarse particles, whereas if it's above 2, that's fine particles. So when we talk about, when we say usually test we do is less than 1 is predominance of coarse particles, above 1 it's predominance of fine particles in the mixture. So we have carbon and dust, for example. So there are several algorithms actually that to calculate the optical thickness. So calculation of optical thickness is the first measure or the primary measure for us to get information about particulate matter from remote sensing. And to do that, we look at the variation of the radiance as function of wavelengths. So the spectral variation of radiance. The different algorithms require different inputs, but mostly they require various wavelengths, including mid-infrared. So if we look at the MODIS product, MODIS has aerosol optical depth product derived from 2 different algorithms. The dark target approach, which is the traditional, let's say the heritage approach to derive aerosols or aerosol optical depth from remote sensing, that assumes that for dark areas, the reflectances at different wavelengths are correlated. So if we know that, we also know that the mid-infrared radiation is not as affected by aerosols than the visible and the near-infrared. So we can calculate mainly the reflectance of the surface in the mid-infrared, then infer the reflectance of the other channels or the reflectance at other wavelengths in the visible, and that help us determine the amount of reflectance that was contributed by aerosol. So we have an inversion algorithm that enables us to get the optical thickness from that difference. The big issue here is that this only works for dark targets. Well, in our area, we don't have many dark targets. It's almost bright. So another algorithm was developed called Deep Blue that assumes that the reflectance appears darker and the aerosol signal appears stronger in the violet blue portion of the spectrum than in the longer wavelengths. Well, however, to do that, you need to have multiple blue channels or multiple blue observations to be able to implement such an algorithm. So not all sensors or not all existing sensors have the capability or can apply this algorithm. MODIS, well, as I said, has 36 bands, including multiple violet and multiple blue. So this was a perfect sensor to apply such an algorithm. By the way, the algorithm itself was developed for CWIFs, which is an ocean sensor. So you'd expect an ocean sensor to have a lot of blue bands, as this is the region that's mostly used or mostly responsive in the ocean. So that's where the idea came from. But then it was expanded over to MODIS to determine this algorithm. So those algorithms were developed, are extracted in an operational way on a daily basis, and to help evaluate them, to help ensure that they give us good numbers, the scientists mainly carry out the validation activities. And most of the validation activities related to aerosol optical depth and aerosol types exploit ground measurements. So there's a network of ground-based aerosol optical depth measurements done through a network called Aeronet. It's a NASA network where sensors or where stations Ground stations like the one shows on the top are implemented. It's a robotic instrument, does the measurements automatically, scheduled to run on the hour. Say do measurements of aerosol at different wavelengths and determine the model, determine the distribution of aerosols. This provides a good input to evaluate those products, and those instruments or this network was used globally to assess the MODIS aerosol product, and turns out to be very the agreement was very high, so errors to within 0.05. In the UAE, we have two of those stations, one in Abu Dhabi city and Masdar, actually, to be more accurate, and one in the western region, in the Dhafra region, in Zara. So I think it will be good to increase the density of this network in the UAE, and I'm looking at the next funding opportunity actually to try to get one of those sensors installed in a lane, because we have a gap there just in the eastern region. So hopefully this will be rectified soon. Now, so if said MODIS has these two algorithms. So if we look at the aerosol optical depth derived over the UV using both algorithms, but well, not surprisingly, the dark target gives us almost an empty map. So couldn't find enough dark targets to inverse the optical thickness. Whereas the deep blue algorithm seems to be producing not a full map, but almost a full map of the UE just for in one day. So you can imagine that if you increase the measurements, this will increase the potential of creating full maps. All right. However, what we need is not the optical thickness, is the PM concentration. So how do we go about converting this AOD, this aerosol optical depth that we measure, that we retrieve from remote sensing into particulate matter concentration? If you look at this graph, the issue is, or one of the first issues is that PM concentrations are measured at the surface level. So that what's used in the indicator or in the index are measured at the surface level. What remote sensing or satellite sensors measure is a column, which is the total concentration through the atmosphere. Just apologize, let me take just a second. So if we need to compare those together, if we need to be able to use the AOD as a predictor for the PM, we need to keep in mind that there are factors that would affect this conversion, mainly the aerosol types and the atmospheric conditions. So atmospheric pressure, humidity, those can affect this conversion. Then the vertical distribution. Because again, what we're measuring is the total from satellite. What we are interested in is at the surface. So we need to look at the boundary layer height, probably the transport, the production, the loss. Then nevertheless, we can look at this from a different aspect. From, let's say, it's a statistical aspect. So we have measurements. We have ground measurements of particulate matter, and we have measurements from satellite. So can we find a statistical relation or a correlation that link them together? And this mainly summarizes, or this is the different approaches that were used by scientists to look at this correlation. By order of difficulty, they start with a simple correlation between two variables. just the PM and AOT or AOD. Then we can start injecting in more variables. So we use a multivariable method to try to improve our estimates. So we think that the land cover, for example, or the aerosol type or the humidity, the water vapor content is a factor. So this can be added as a variable in the mix. And then, like everything else, artificial intelligence and deep learning is also hitting these approaches. So we can look at all sorts of factors that can affect our conversion. Just dump that into a machine learning neural network and come up with the best value, with the best estimate for PM. So this approach is gaining a lot of steam nowadays and using very good results. The only issue with that, well, it's not a real issue. Well, it is a real issue, but not for prediction. The only issue is it's difficult to explain why things work or what factors are affecting more than others. Then the last approach is by using a model surface aerosol concentration and look at the results of that model. So through modeling, through climatology, we look at what the climatology gives us, or we're supposed to get from the climatology, versus what we get in reality. And that gives us an estimate of the PM. So I said just one we did with students. We started looking at just the aerosol, modest aerosol mainly, and try to predict PM10. The idea is to do that actually for the whole country, but then we started small with just the Alain region. So in Alain, we have six stations, maybe 6 air quality stations that are operated by EA. So we used the data collected in 2018 to look at that. And if you look at the type of areas that are covered, where these stations are, they are fairly similar. So we just the points or the dots that you see on the map are the location of those stations. So again, they are concentrated in the city. That if you try to do say an interpolation of the data that are collected to fill your region, so you notice that the values are much higher in the summer, and this is what we expected. That's where we have the dust events. So comparing those, just or doing average monthly PM measurements from the ground stations and comparing those to the MODIS AOD, you show that there's a very good, at least the variations are similar in both graphs. So so we just went with a simple 2 variable correlation approach, or the simplest approach, where we get MODIS data, we have PM10 measurement. We try to find a regression that works and maybe define a prediction equation for PM10. So we did that for the different stations, and then we combined, so looking at correlation between PM10 and aerosol, and then we finally combined all 6 stations together, come up with a model that we can apply to our region. Then from there, we take the MODIS inputs and we derive the PM10 for the whole area from MODIS. So this is, I would say this is work on progress. Actually, we're looking at expanding the model, looking at the factors that affect the performance of the regression, just increasing the accuracy and I'm sorry, the accuracy of our model and our estimate. So in conclusion, I would say remote sensing can be used to predict air quality indicators and fill the gaps where we don't have air monitoring stations. There are some limitations of remote sensing that need to be recognized. So we have, since we rely on optical sensors, we have acquisition during daytime only. We have low temporal resolution compared to air monitoring stations. And then we have, we measure total column retrieval rather than surface. So those need to be just kept in mind. So more complex, probably models, prediction models taking into account these different factors would improve the quality of the prediction. And finally, the advent of aerosol products from geostationary platforms goes 16 and later, and Meteosat 8 and later, actually provides a great opportunity to have a much higher temporal resolution for the aerosol optical depth and aerosol type retrieval, as these sensors can easily provide a measurement every hour, just hourly measurement. So matching mainly the measurement of the air quality station. With this, I'd like to stop here and thank you for your attention. You have, be happy to answer any question you have.
Thank you, Dr. Nazmi, for your beneficial presentation. As you just stated, it is time for our audience to ask questions. Can we raise hand if you have any inquiries?
So it looks like there are some questions actually on the chat. So yeah. In our study, actually, just to answer Dr. Diana, at this point, we consider that we don't necessarily consider that all the aerosols are from dust, but the measure itself, the PM10, includes fine and coarse particles. Looking at the source of the dust and the timing, in the case when we have that in the summer, mainly in July was the peak, that is definitely related to dust events. Then there's a question about the use of AI and deep learning.
How can AI and deep learning be helpful in analyzing the information?
Okay, so I think I mentioned that. I said this is where the regression is moving forward, or the prediction approaches are relying on that, are using machine learning algorithm where we input all of our ingredients, so the satellite measurements in addition to other environmental measurements, and try to get a better prediction.
We have another inquiry from Mr. Mohammed Yagoub with regard to the weather currently now, the season of summer.
I'm sorry, I couldn't hear you.
Mr. Mohammed Yagoub.
Oh, okay. All right, so he's asking about temporal. Okay, summer and spatially. Well, the idea of using remote sensing was to do the spatial distribution and try to do that. Unfortunately, as I said, this is a project that we just it's just at its start. We haven't analyzed that enough to give you an answer. But ultimately, this is what we want to get is measurement for the whole area.
Perfect. Another question here will allow Mr. Abdelkader to ask.
Okay. Hey, Salam, do you hear me?
Yeah, I can hear you.
Okay, Salam, okay. So the correlations are really high. You know, I tried this before with each single station. Yeah. And I was lucky if I got a correlation of 0.3. So how did you you did each station alone, like the PM10, for example, measured from a station correlated with AUD above the station, or all the 6 together at one time?
Well, we did both actually. The graph that I showed first with all of them, and probably I rushed it because I saw that the time was passing. We got less correlation when we did the individual stations. I guess because we didn't have enough points. But when we combined them together, that's where we increased the correlation. Another thing is it depends which algorithm you use for optical thickness and the resolution. So here in this study, we use the 1 kilometer product actually, rather than the 10 kilometer.
The 10 kilometer, not the 1 kilometer.
No, you use the 1 kilometer.
Use the 1 kilometer.
Yeah, the MIAC.
MIAC, yeah. Okay, great, thanks.
Okay. And see that the question from Dr. Ahmed Bentog. Can you use targets for each contract? Well, they are the PM10 stations. The air monitoring stations are there to monitor the quality of your air. Well, ultimately is to try to alert people to hazard to their health. Can the stations themselves, the monitors, be used to reduce the PM10? No, they cannot, because the source of PM10, of the source of particulate matter, is not cannot be controlled by a sensor. They are due to natural processes and to anthropogenic processes. So if we want to control those, we can probably play on the anthropogenic, the man produced pollution, but we cannot stop desert events, desert storms from happening, and that will inject dust in the atmosphere. We can monitor it, as I said, and we can, in that case, we can just try to identify what's happening around. Well, the interpolation actually gave, I wouldn't say high accuracy because of the limited number of stations, but then to do that, to improve it, actually, we had to use more than the 6 stations, and what's around them in the different outside of the study area. But again, with the small number of patients, the interpolation is not going to do miracles.
Final question, Doctor, just to wrap things up, from two attendees, Mr. Oriel and Dr. Hamad. It's basically the same question, which is how do you differentiate between PM10 and PM2.5? And if you can explain how you can differentiate and in which PM size you have better results.
Okay. Well, to differentiate between them, I mean, are we talking about how they are measured or what they are? Because the definition, I think I gave it in the presentation. So what is considered as 2.5 are fine particles that are less than 2.5 micrometer in diameter. Now, how they are measured, let me just try to go back to one sensor. Put the sensor group. Okay, here we go. So the example, I didn't talk much about it because of time. The figure on the upper right corner is a sketch for what's called the compass mainly a flow controller, in which we have air is being sucked into this sensor. And then there are filters that separate the particles that are in the air into fine and coarser mode. So the fine particles will go on one side of the sensor, whereas the coarse particles will go on the other. And then the flow of these two, the flow of the coarse and the fine particles, is measured at the output of this device, and that's what gives the concentration of the concentration of PM10 or PM2.5.
Sounds good. Thank you, Doctor. We came to the end of today's webinar. Thank you all for your kind interest in attending, and we look forward to have you at our upcoming events, inshallah. Thank you for your time, Doctor.
Thank you.